Welcome to Chapter 8, Chi-Square and Nominal Data, the video series hosted by me, Tim Smith, on the Workbook of Quantitative Tools and Techniques in Marketing, 2nd edition. First of all, let's make it clear here. We pronounce this as chi squared. That is like chi, K-I square, as in normal square. We often write it using the Greek letter chi, that's the X looking thing, squared, because it's chi squared. I never want to hear you say chi squared or chi. It's chi, hard k sound, okay? Got it. Now what are we going to use with chi squared? Well, when we think back about our F test and our T test, which we looked at in prior chapters, those tests are used to identify statistical significance of differences in numerical data between samples. In chi-square, we're using nominal data. So we're trying to identify the statistical significance of differences in nominal data. So, as a reminder, t-test for 2 samples, numerical, f-test for 3 or more samples, numerical, and chi-square for nominal, that's categorical type data. So the example of which you use it is you got 2 groups, 2 samples, from which people either purchased or didn't purchase. So the act there is they purchased and they didn't purchase. And group A, we might see 50 purchases and 100 no purchases. And group B, we might see 52 purchases and 49 no purchases. And we're trying to figure out if group A is like group B or group A is not like group B. There's the example. Now, how are we going to do this? We're going to start by looking at the observed data from the 2 different samples, and then calculate what you would have expected if the 2 samples were from the same population. So what would you have seen if the 2 samples were from the same population? What should you have expected? And how are we going to find that? How are we going to calculate that? We're going to take weighted averages to compensate for differences between potential differences and the sample sites. And say, okay, well, on average, how many, across group A and group B, on average, how many people purchased? That gives you the probability of purchasing. And how large is group A? That tells you how many we would have expected to see in group A. And how large is group B? After we do this calculation using the observed to calculate the expected, we'll simply do a little chi-square test. More specifically, we'll be looking at the p-value of the chi-square test because, well, Excel and other statistical software will calculate all of these chi-square values. They'll find the critical values, and then from there we can find the p-value, or we can just let Excel do it directly for us and say, hey, what's the p-value of this chi-square test? And make a conclusion using the hypothesis test, just as we've done in the prior 2 chapters. Degrees of freedom is going to come up again, and with the degrees of freedom in chi-square is calculated by looking at the number of samples, less 1, times the number of categories, less 1. If you have them set up in rows and columns, you can state it as simply rows minus 1 times columns minus 1. And that will tell you the degrees of freedom in a chi-square test. We must at least have 1 degree of freedom, but sometimes we have more. Now, let's look at this in Excel. Here is an example of 2 groups, Group A and Group B, and their purchase or no purchase data. This is our observed data. So we know how many people purchased in Group A, we know how many people purchased in Group B, we know the no purchase rate in Group A and no purchase rate in Group B. We're going to come down here and calculate the expected outcome. between group A and group B. To make my life easier, I'm just going to copy and paste all of this so that the header's already there, and then delete the data. Now, how are we going to get the expected? Well, we said we were going to take weighted averages. Yep, we are. To find those weighted averages, we're going to take the sums. So this be equal to the sum of these two and the sum of those two. And we'll take the sum also across the rows equal to the sum of those two. So that's the total size of group A. That's the total size of group B. And this is the total size of everything. All right. So on average, if group A and group B were the same, we would have 60 out of 2760 purchases, right? But group A is only 1327 large. So for group A, I have it I expect to see 60 out of 2760 purchases, right? That's my percentage of purchases. I could put it in percentage format, or not. And how large is group A? Well, it's 1327. So I want to get rid of those extra decimals. We don't need that. We would have expected about 29 purchases in group A if group A and group B were the same. Because 60 out of 2760 times you purchase, and this is the size of group A, so I'm just taking a weighted average or an expectation. I can use this same formula. Let's take a look at what I did. I took this, I divided it by that, and I multiplied it by this. I could have also had said, I am going to take this, multiply it by that, right? And then divide it by the total. You end up with the same thing. This divided by that, then times this, is the same as this times this divided by that. Nice law of multiplication. So there we have our no purchase rate. You see you get the same number. I'm sorry, I calculated the purchase rate there. And you see you get the same 29. I'm going to copy and paste it. Just put it right over it. Next, I'm going to make it easy for me to copy and paste it everywhere. Control Z, let's try again. Dollar signs where they belong. I'm going to want to hold this column constant, and I'm going to want to hold this row number constant. Copy and paste. So I would have expected 29 purchases from group A and 1,298 no purchases in group A. However, I got 1,290. I would have expected 31 purchases in group B, but I got 23. So I got far more purchases in group B. Far fewer were observed than what I expected. And then in terms of no purchases, it was about the same. Great. Now we need the p-value of the chi test. How are we going to get that? We simply type in equals chi square, right? And notice you got all of these parts. We just want the test. Returns the test for independence, the value from the chi-square distribution for the statistic, and the appropriate degrees of freedom. I want that one. Chi-square dot test. Open parentheses. Then it says give me the actual range. So there's the actual data. And the expected data. So this is the expected data. Close the parenthesis. Return. And I got 0.03. So that's the p-value for my chi-square test. What's my alpha? You know, it's 0.05, 5%. So my p-value is less than my alpha. Therefore, I'm going to have to say the differences are statistically significant. Right? First, I reject the null hypothesis. I accept the alternative hypothesis. The differences are statistically significant. Good. Well, which one is bigger? Which one purchases more on average? That's a good question. Purchase rate, otherwise known as win rate. So what's my win rate? Well, I win 37 out of 1327 here, and I win 23 out of 1423 there. So there we go. I can put that in terms of percentage, add another decimal, and we can say, well, which one wins more? Where do I get more purchases? That's Group A. Excellent. So Group A purchases more often than Group B. I can also add that Group A purchase rate is 2.8%. Group B purchase rate is 1.6%. And we've interpreted our data. Pretty straightforward. That is a chi-squared test. Now let's think about the degrees of freedom. And let's look here. How many rows do we have? Well, we have 2 rows. So rows is 2. How many columns do we have? Columns. Well, we have purchase or no purchase. 2. So when we're looking for our degrees of freedom, that is the number of rows less 1 times the number of columns less 1, otherwise known as 1. We didn't have to do all that multiplication. We could have figured that one out. That's a very simple example of a chi-squared test. Now, since we have this up here, what if we had had a different purchase rate? This is the way it's presented in the book, but what if we had had a different purchase rate? What if Group A only purchased 20 times? Well, in that case, the p-value of the chi-test is 86%. We would have accepted it. And these two purchase rates are pretty similar. What if it was 14 times? It's getting closer to rejecting the null hypothesis. What about 10? Now I would have rejected the null hypothesis at 0.8 and 1.6%. This is an example of why you would want to use chi-square. I mean, is 10 really that different from 20 when you're looking at something on the order of 1400? It's hard to say. But the chi-square test actually enables you to say, yeah, 10 is significantly different than 20. It's very nice. What if this was only 20? Then we couldn't tell the difference between 10 and 20. But 10 and 22, 10 and 23, there we go. Then we can tell the difference. Let's put this back to 37, because that's what we had as the original problem. And you see there with a 37 versus 23, or a 2.8 versus 1.6 win rate, we know that there's a difference because our p-value of our chi-square test is less than 5%. It's only 3%. Good deal. Let's look at another example. Here we have different age groups in 2 different locations, the current and the proposed. Now, in this case, we have 4 columns. So when we calculate out here, rows versus columns, on this case, our rows is 4, but our columns is still 2. So our degrees of freedom is going to be equal to the number of rows less 1 times the number of columns less 1, or 3. Our degrees of freedom in this case is 3. How would we do the chi-squared test? I'm going to have to move this over here. And let's go ahead and copy and paste all of this down here so I can type in expected. We would do the same thing once again. we'd find the sums going up and down equals sum of everything. Copy, paste, equals sum of across. Copy, paste, get the grand total of 534 pieces of data. And now we'll calculate out what we would have expected. Well, this is 271 out of 536. 271 times 105 divided by the total size, or 536. So while this group has 105 members on it, we're winning 271, or C7, out of 536. So that would be the expected total here. Let's get rid of those extra decimals. We don't need them. We can similarly put in our dollar signs to hold certain things constant as we move around. And I'm being very careful to make sure I put them in the right place. Copy and paste. And let's find once again, the p-value of a chi-test. So p-value of chi-test, and that would be equal to chi-square dot test. Again, the actual range, comma, the expected range, close parenthesis. There we have it, 78%. Well, this is definitely above my alpha of 5.05 or 5%, so therefore I'm going to accept the null hypothesis. The two sample are from the same population. And in this case, what we're looking at is two possible locations, the current and the proposed. And suppose that the vendor is successful in the current, he's looking at the proposed, and they think that age is what makes the current location successful, the age profile of the people in the area. If the age profile is what makes the current location successful, the new proposed location has a similar age profile. This marketer can expect the proposed location to be successful. So what's the conclusion you would tell this marketer? The proposed location has a similar age profile as the existing location. If age profile determines success, the proposed location should be successful. But do you really think age determines success? Maybe. It kind of works if you're targeting youth and you need to make sure you have enough young people there. For instance, playground. Or if you're targeting elderly and you need to make sure you have enough elderly people in the new location. Or if you're targeting family activities. Yeah, maybe. Absolutely. Well, that's an example of chi-square, both with, just back here, just two samples, A and B, or back here with 4 samples. But now we're just looking at 2 different locations. Or one would say that there's 2 samples here, but 4 different categories of answers. And one could say here, there's 2 samples here and 2 different categories of answers. Notice here my categories of answers are going across, whereas here my categories of answers are going down. Chi-square doesn't really care if it's going across or down. It does care to make sure that this setup and this setup are laid out in the exact same manner for Excel to do its work here with this function. With this knowledge, you should be able to do, at the end of Chapter 8, the exercises on cold calls, PBS viewers, Starbucks, morning or evening selling, male or female photos,